sac123 problem number 1. Get a bucket of water raised from a well by means of a hand crank. Get mass of bucket plus contents, moment of inertia of the hand crank, and when the bucket is 11 meters above the water level, the hand crank is released from rest. The bucket falls, rope unwinds, hand crank spins faster and faster, and they want to know how fast it's going at that instant just before the bucket hits the water, how fast the hand crank is spinning. This is a conservation of energy problem. We'll consider the before picture, that instant when the hand crank is released. We've got a bucket in the picture. We give it 2 handles here, and the rope is wrapped around this hand crank. In the before picture, we'll put the bucket up at a height, let's call it Y0, above the reference level, and that's the lowest point it ever gets to, which I think I'll put this as the water level down here, just a little bit below that. I am going to work with the center of mass location in this one. And it's got, I call this omega 0, the spin rate of the hand crank is equal to 0, and V0 is equal to 0. Nothing is moving there. Okay, then in the after picture, the bucket is all the way down here. It's moving very rapidly. I'm actually going to go with V and V prime, so I'll go ahead and scratch these zeros here. So omega and omega prime. I'll even go Y and Y prime. I have the hand crank spinning rather rapidly. At a rate I'll call omega prime. And bucket is at the reference level. So it has indeed dropped 11 meters. Y itself is 11.0 meters. I want to check that. I think they said it was 11 meters above the water to start with. Yep. M, put that in a different color. The mass of the bucket is 12.0 kilograms. Moment of inertia of our hand crank is 0.850 kilogram meter squared. I think we've got all we need. We recognize that we've got energy of motion in terms of translational motion, the falling, moving along a straight line path, and energy of motion associated with the rotation as well. Let's write down our conservation of mechanical energy equation. The original energy is equal to the final mechanical energy. E is equal to E prime. We got I think I'll put down 2 types of K and 1 type of U on both sides. Over here, I'll call it K prime and U prime. And we got kinetic energy of rotation and translation. The rotation, the spinning motion, translation, moving along a straight line path. And we've only got one kind of potential energy, so I don't need a subscript, just the gravitational potential energy. Alright, let's think about what's zero. It's not spinning, so there's no kinetic energy of rotation in the before picture. So that's zero. The bucket is not moving, so that's zero. It is up high, so we do have some gravitational potential energy. In the after picture, the bucket is moving, and so we get kinetic energy of translation, and the hand crank is spinning, so we've got kinetic energy of rotation, but it's not up high. It's at the reference level, so we got zero potential energy. The gravitational potential energy is mass of the bucket times G times H. I'm not paying any attention to the gravitational potential energy of the hand crank because it stays at the same level at all times. I'll think of it as having its own reference level. It's not undergoing any translation, so I don't have to worry about its potential energy. I could put mass of the hand crank times GY on both sides, and maybe I have to give it some other name, maybe Z for the height, but it's at the same height in both cases, so I'd have the same mgz on both sides of the equation. They cancel each other out. Better to just ignore it. It's not going up and down, so we don't have to worry about the potential energy of the hand crank. But the potential energy of the bucket I've got in there, I'm actually calling that height of the bucket initially above the reference level Y, so I'll leave that as a Y. And then on this side I got 1/2 I omega prime squared for the kinetic energy of rotation of the hand crank plus 1/2 mv prime squared for the kinetic energy of translation of the bucket. And they tell us that in the after picture the bucket is falling at 1.10 meters per second. So I'll go ahead and record that in the diagram. And I'm supposed to be solving for omega prime. So let's start getting that all by itself. I'll multiply both sides by 2, I think, to start with. Get rid of the fractions. 2mgy equals I omega prime squared plus mv prime squared. And then I'll subtract the mv prime squared from both sides and swap sides. So I have I omega prime squared was on the right, now on the left. And on the left, after the subtraction, I had 2mgy minus mv prime squared. Divide both sides by I. And I think I'll factor out an m from the top there. I got an m in both terms. Factoring that out, I can write that as m over I times 2gy minus v prime squared. Just makes it so I only have to plug in the value of m into the calculator once. And then omega prime squared is square root of m over I times 2gy minus v prime squared. So now I just have to substitute values and evaluate. Didn't need to write the square there. I took the square root of both sides to get rid of that. So I've got omega prime is equal to the square root of, I'm going to substitute the values, the mass of the bucket is 12 kilograms. And the moment of inertia, I believe, was 0.850 kilogram meter squared. Yep. And at 2 times 9.80 meters per second squared times the y was 11 meters, and then minus v prime 1.10 meters per second. And it's squared. And taking the square root of all of that. And that evaluates to 55 radians per second. 55.0 radians per second. That's our answer. If you want to, you can convert that into revolutions per second. That corresponds to 27.5 revolutions per second. Or even RPM, revolutions per minute. It's 1650 RPM, in case you want to compare it to your tachometer readings. But omega in SI units is given as 55.0 radians per second in this one.